You're standing at the launch pad. Behind you, Earth, everyone you know, your entire life. Ahead, Proxima Centauri, the closest star beyond our sun. Do you board? Because this isn't a trip to Mars. This is a one-way ticket into the unknown, where time, distance, and reality itself become your enemies. If you're the kind of person who looks up at the night sky and wonders what's really out there, please hit that subscribe button. Now let's get started. Proxima takes about 550,000 years to complete one orbit around its stellar companions. It's a cosmic family, bound by gravity across a gulf of space that to us seems impossibly vast. Now let's talk about the journey itself. The Voyager 1 spacecraft, humanity's most distant emissary, launched in 1977 and is currently traveling at about 17 kilometers per second relative to the Sun. That's fast, truly fast by human standards, roughly 61,200 kilometers per hour. Yet at that speed, Voyager would take over 73,000 years to reach Proxima Centauri. If it were even headed in that direction, which it isn't, 73 millennia, that's longer than all of recorded human history. The pyramids of Giza would still be under construction when your spacecraft was only halfway there. Clearly, we need to go faster, much faster. This is where concepts like breakthrough Starshot entered the conversation. Announced in 2016 by billionaire Yuri Milner, breakthrough Starshot proposed sending thousands of tiny spacecraft, each weighing only a few grams, equipped with light sails. These nanocrafts would be accelerated by powerful Earth-based laser arrays, pushing them to 20% the speed of light. At that velocity, the journey to Proxima Centauri would take about 20 years, plus another 4.2 years for their data to reach us back on Earth. The program aimed to prove the concept was possible, to identify potential showstoppers and find credible solutions. Recent reports have suggested breakthrough Starshot has been paused or even failed, but that's not quite accurate. Phase 1 of the project successfully met its stated objectives. It identified major technical challenges, from building gigawatt-scale laser arrays to engineering sails that could survive the intense beam without vaporizing, to the problem of communicating across light years with a transmitter the size of a postage stamp. The project produced numerous peer-reviewed papers and demonstrated that, while extraordinarily difficult and expensive, interstellar travel using laser-driven sails isn't physically impossible. The program is on hold while seeking broader support and restructuring for future phases, but the groundwork has been laid. Even more recently, in 2026, scientists published proposals for sending swarms of these laser sail spacecraft to Proxima Centauri. Each tiny probe would carry a camera, and together, acting like a distributed interferometer, they could capture gigapixel resolution images of Proxima b at 20-meter resolution. Imagine seeing surface features on an alien world orbiting another star. That's the promise if the engineering challenges can be overcome. But let's be honest, a flyby mission with gram-scale probes is one thing. A crewed journey? That's an entirely different beast. If we're talking about sending humans, we're talking about a spacecraft massing at least tens of thousands of kilograms, probably much more. You'd need life support, radiation shielding, propulsion, habitats, food, water recycling, power generation, and redundancy for everything. You'd need a ship that could sustain a crew for years, possibly decades or even generations, depending on the propulsion method. Let's explore what the terrifying truth about interstellar travel really means. I've got a whole video dedicated to the darker, more unsettling realities of leaving our solar system, and I highly recommend checking it out after this one. It dives deep into the psychological, biological, and existential challenges that don't get talked about enough. It's on the card above and pinned on the comments. To make this voyage remotely feasible within a human lifetime, you'd need to accelerate to a significant fraction of light speed. Let's say, for argument's sake, you could sustain a constant acceleration of 1 g, that's 9.81 meters per second squared. The same gravity you feel standing on Earth right now. This would keep the crew comfortable, avoiding the bone loss and muscle atrophy of prolonged weightlessness. But even at 1 g of constant acceleration, the mathematics of relativity start to twist time and space in remarkable ways. Using the equations of relativistic motion, if you accelerate at 1 g for half the journey, then flip your spacecraft and decelerate at 1 g for the second half, something called brachistochrone trajectory, you could reach Proxima Centauri in about 3.5 years of ship time. That's right, 3.5 years as experienced by the crew. But here's the twist. Back on Earth, about 6 years would pass. This is time dilation, one of the strange and beautiful consequences of Einstein's special relativity. The faster you move, the slower your clock ticks relative to observers at rest. At 20% the speed of light, the kind of velocity breakthrough Starshot nanocrafts aimed for, time dilation is barely noticeable, but push closer to light speed and the effect becomes profound. If you could somehow reach 90% the speed of light, a journey to a star 100 light-years away might take only about 20 years for you, but 100 years would pass on Earth. You'd return to find everyone you knew long dead, civilizations risen and fallen, history rewritten. This isn't science fiction, this is physics. But before we get lost in the poetry of relativity, we need to confront a brutal reality. Getting to those speeds requires energy, staggering, almost incomprehensible amounts of energy. Let's put some numbers to this. The kinetic energy of an object increases with velocity, but once you approach relativistic speeds, the relationship becomes exponential. To accelerate even a small spacecraft, let's say 1,000 kilograms, that's roughly the mass of a compact car, to just 10% the speed of light, you'd need about 4.5 times 10 to the 17th joules of energy. To put that in perspective, that's about the total energy output of a large nuclear power plant running continuously for roughly 4.5 years. And that's just to reach 10% light speed with a tiny uncrewed probe. Now scale that up. Imagine a crewed interstellar ship massing 50,000 kilograms. That's still modest by spacecraft standards. To push that to 20% light speed, you're looking at energy requirements in the range of 10 to the 19th joules, equivalent to several hundred megatons of TNT. The entire annual energy consumption of a country like the United Kingdom would barely cover it. And remember, you also need to decelerate when you arrive, so double those numbers. This is why conventional rocket propulsion simply doesn't work for interstellar travel. The tyranny of the rocket equation formulated by Konstantin Tsiolkovsky over a century ago tells us that the fuel requirements grow exponentially with velocity. To carry enough chemical fuel to reach even a small fraction of light speed would require a fuel tank millions or billions of times more massive than the spacecraft itself. It's physically impossible with chemical rockets. So what are the alternatives? Nuclear propulsion offers higher energy density. Fusion rockets, if we can ever build them, would be better still. Antimatter, if we could produce and store it safely, offers the highest energy density possible from conventional matter. When matter and antimatter annihilate, they convert mass directly into energy with 100% efficiency, following Einstein's famous equation, E equals mc squared. Even a few grams of antimatter could propel a spacecraft to impressive speeds. But here's the problem. We currently produce antimatter in particle accelerators at a rate measured in nanograms per year, and it costs trillions of dollars per gram. It would take us centuries with current technology just to produce enough antimatter for a single interstellar mission, and we still don't have a reliable way to store it for long periods. Then there are more exotic concepts. Laser sails, like those proposed by breakthrough Starshot, sidestep the fuel problem entirely by leaving the power source behind on Earth or in orbit. You shine an incredibly powerful laser at a reflective sail attached to your spacecraft, and the photon pressure accelerates it. No fuel needed on board. The challenge becomes building a laser array powerful enough, keeping it focused across millions of kilometers as the craft accelerates away, and engineering a sail that won't simply vaporize under the intense beam. We're talking about laser powers in the gigawatt to hundreds of gigawatt range, focused with extraordinary precision. Other ideas include magnetic sails that ride the solar wind or interstellar magnetic fields, ramjets that scoop up hydrogen atoms from space and use them as fusion fuel, and even more speculative concepts like warp drives that bend space-time itself, though those remain firmly in the realm of theoretical physics with no clear path to implementation. The point is this: every single propulsion method we've conceived for interstellar travel involves technology far beyond our current capabilities, energy sources we can barely imagine harnessing, or both. This journey isn't just ambitious, it's at the very edge of what physics allows. But let's assume, for the sake of exploration, that we solve the propulsion problem. Let's say humanity develops fusion drives or antimatter engines or perfects laser sail technology for larger craft. You've got your ship, you've got your propulsion, you're accelerating toward Proxima Centauri at a meaningful fraction of light speed. What happens next? You enter the void, true deep interstellar space. And this is where most people's imagination of space travel falls dangerously short. We think of space as empty, a vacuum, nothingness. But interstellar space isn't truly empty. It's filled with gas, mostly hydrogen and helium at incredibly low densities, typically around 1 atom per cubic centimeter in the local interstellar medium. That sounds like nothing, and by everyday standards it is. It's a better vacuum than anything we can create in laboratories on Earth. But when you're traveling at 10, 20 or 30% the speed of light, even that incredibly diffuse gas becomes a hazard. Why? Because of relativity. As you accelerate, those stationary hydrogen atoms, from your perspective, are rushing toward you at relativistic speeds. A hydrogen atom hitting your spacecraft at 20% light speed carries kinetic energy equivalent to a high-speed bullet, scale that up to the trillions of atoms your ship would encounter every second, and you're facing a continuous bombardment that generates heat, erodes materials, and produces secondary radiation as atoms smash into your hull. Scientists who studied this problem for breakthrough Starshot calculated that even the gram-scale nanocrafts would heat up from collisions with interstellar hydrogen. For a crewed ship with a larger cross-section, the effect would be far more severe. You'd need shielding, substantial shielding, at the front of your spacecraft. Some proposals suggest using magnetic fields to deflect charged particles, essentially creating an artificial magnetosphere like Earth's. Others propose placing expendable material, ice or metals, at the front to absorb impacts. But all of this adds mass, which requires more energy to accelerate, which brings us back to the propulsion problem. Then there's cosmic radiation. Galactic cosmic rays are high-energy particles, mostly protons and atomic nuclei, accelerated to near light speed by supernovae and other violent cosmic events. They permeate interstellar space. NASA's Voyager 1, which crossed into interstellar space in August 2012, has been measuring these cosmic rays directly. The data show that galactic cosmic ray intensity in the local interstellar medium is about 15 times higher than what we experience inside the heliosphere, the protective bubble created by the solar wind. For a crew on an interstellar journey, this radiation is a serious threat. Cosmic rays can penetrate spacecraft hulls, damage DNA, increase cancer risk, and cause acute radiation sickness during solar particle events, or if the flux suddenly increases. Over a multi-year journey, the cumulative dose could be lethal without adequate shielding. Water, hydrogen-rich materials, and polyethylene offer some protection, but again, you're adding mass. There's always a trade-off, and here's another relativistic twist. As your spacecraft accelerates, cosmic rays don't come at you uniformly from all directions anymore. Relativistic aberration causes them to appear increasingly concentrated ahead of you, beaming forward into a narrow cone. The faster you go, the more intense this forward-directed radiation becomes. At very high speeds, the radiation field in front of your ship becomes a blazing wall of high-energy particles. Some physicists have calculated that at speeds above about 90% light speed, the radiation flux could become so intense that it would kill an unprotected crew almost instantly. You'd need meters-thick shielding just to survive, and even then the long-term exposure would be extremely dangerous. So you're battling interstellar gas, cosmic rays, and the strange effects of relativity itself, all while hurtling through a void so vast that light, the fastest thing in the universe, takes over 4 years to cross it. Let's talk about navigation. At interstellar distances, you can't just point your ship at Proxima Centauri and go. Stars move. Proxima has a proper motion, the term for a star's apparent movement across the sky, of about 3.8 arcseconds per year in right ascension and 0.77 arcseconds per year in declination. Over the decades your journey would take, Proxima will have shifted position noticeably. You'd need to aim not at where it is now, but where it will be when you arrive. This requires precise astrometry, the measurement of stellar positions and motions, something the European Space Agency's Gaia mission has been doing with exquisite precision. Then there's the question of course corrections. Any tiny error in your initial trajectory, even a fraction of a degree, compounds over light years into missing your target by billions of kilometers. You'd need navigation systems that can track your position relative to multiple stars, calculate corrections, and adjust your course mid-flight. But every course correction requires propellant or energy, resources you can't easily replenish. There's no refueling station halfway to Proxima and communication. At the speed of light, a radio signal from your ship near Proxima Centauri would take 4.24 years to reach Earth. Ask Mission Control a question, and the answer arrives 8.5 years later. You're on your own. Every decision, every emergency, every malfunction has to be handled by the crew without support. The psychological weight of that isolation is almost unimaginable. We like to think of astronauts as brave explorers, and they are. But the astronauts we've sent to space so far have always known Earth is right there, visible through the window, a communications delay measured in seconds or minutes at most. On an interstellar voyage, Earth becomes a pale blue dot, then a star among stars, then invisible to the naked eye. The sun itself fades to just another bright point of light. You are truly, utterly alone in the dark. Now let's dive deeper into what life aboard an interstellar vessel would actually be like, because this is where the romance of space exploration meets the grinding reality of human biology and psychology. First, consider the size of your spacecraft. For a journey lasting years or decades, you can't just pack people into a capsule like we do for trips to the International Space Station. Astronauts on the ISS endure cramped quarters because their missions last months, not years, and they can see Earth through the window. They know they're going home. An interstellar crew needs space, genuine living space, or they'll go insane. Psychologists who study long-duration spaceflight, drawing on Antarctic research stations and submarine missions, suggest you'd need at least 15 to 20 cubic meters of personal space per crew member, plus communal areas, exercise facilities, medical bays, laboratories and agricultural sections if you're growing food. For a crew of even 10 people, you're looking at a habitat module massing many tons. Add life support systems, power generation, propulsion, fuel or energy storage, shielding, and redundant backups for everything critical, and your spacecraft quickly balloons to hundreds of tons or more. The life support system alone is a massive engineering challenge. On Earth, nature recycles everything. Plants convert carbon dioxide into oxygen. Water evaporates, forms clouds, and rains back down. Bacteria decompose waste, returning nutrients to the soil. On an interstellar ship, you have to replicate these cycles artificially in a closed system with near-perfect efficiency. Even tiny losses add up over years. The ISS recycles about 93% of its water, recovering it from humidity in the air, crew sweat, and even urine. That's impressive, but it still requires regular resupply from Earth to make up the losses. An interstellar ship has no resupply. You'd need to push recycling efficiency to 99% or higher and maintain it flawlessly for years. A single major failure in your water recycling system could be catastrophic. Oxygen presents similar challenges. You can electrolyze water to produce oxygen, but that requires energy. You can grow plants or algae to generate oxygen through photosynthesis, but then you need to provide light, nutrients, and manage an entire ecosystem. Some proposals suggest carrying compressed oxygen or chemical oxygen generators as backups, but again, that's more mass. Food is perhaps the most difficult resource to manage. An adult human needs roughly 2,000 to 2,500 calories per day, about 1 kilogram of food. Over a 10-year journey, one person consumes roughly 3,650 kilograms of food. Multiply that by your crew size, and you're looking at tens of tons of provisions. You could carry freeze-dried or preserved food, but that's a lot of mass and takes up valuable space. The alternative is growing food aboard the ship, bioregenerative life support systems, where you cultivate crops in hydroponic or aeroponic chambers, offer a way to produce food, recycle air, and even provide psychological benefits. Astronauts consistently report that tending plants in space is emotionally soothing, a connection to life and growth in an otherwise sterile environment. But growing enough food to feed a crew requires significant space, energy for lighting, water, nutrients, and careful management to prevent disease or crop failure. You're essentially maintaining a farm in space. If a blight wipes out your wheat crop halfway to Proxima, your crew faces starvation. Then there's the human body itself. We evolved under Earth's gravity, bathed in Earth's magnetic field, with a 24-hour day-night cycle. Take us out of that environment, and problems emerge. In microgravity, bones lose density at a rate of about 1 to 2% per month. Muscles atrophy. Fluids shift toward the head, causing puffy faces and vision problems. The cardiovascular system weakens because it doesn't have to work as hard to pump blood. Astronauts on the ISS exercise 2 hours every day just to slow these effects, and they still return to Earth weakened, requiring weeks or months of rehabilitation. This is why constant acceleration is so appealing for interstellar travel. If your ship accelerates at 1 g continuously, you have artificial gravity. The crew can walk, exercise, and live normally. Their bodies won't deteriorate, but maintaining 1 g of acceleration for years requires enormous amounts of energy, bringing us back yet again to propulsion challenges. Most realistic interstellar ship designs involve periods of acceleration followed by long coasting phases in microgravity, then deceleration at the end. During those coasting years, the crew would face all the health problems of prolonged weightlessness. One solution is rotating habitats. Spin your spacecraft or a section of it, and centrifugal force creates artificial gravity. This has been proposed since the early days of space exploration. The challenge is engineering. A rotating structure experiences stresses that a static one doesn't. You need bearings, seals, and mechanisms that can function flawlessly for years in the harsh environment of space. The rotation rate has to be slow enough to avoid disorienting Coriolis effects, which means you need a large radius, which means more mass and complexity, and then there's radiation again. We touched on cosmic rays, but let's dig deeper into what that radiation does to the human body. High-energy particles tear through cells, breaking DNA strands. Most of the time, cellular repair mechanisms fix the damage, but not always. Accumulated damage increases cancer risk, accelerates aging, and can cause cataracts, cardiovascular disease, and central nervous system damage. Some studies with mice exposed to simulated cosmic ray radiation showed cognitive impairment, memory loss, and behavioral changes. Imagine your crew halfway to Proxima, starting to show signs of dementia or personality shifts due to radiation exposure. There's no hospital, no advanced treatment. You're on your own. Shielding helps, but perfect shielding is impossible without enormous mass. Water walls, polyethylene-rich materials, and magnetic deflection systems can reduce exposure, but not eliminate it. Some radiation always gets through. Crew members on an interstellar voyage would be accepting a significantly elevated cancer risk, along with other long-term health effects we probably don't fully understand yet. They'd be pioneers in the truest sense, accepting dangers that could shorten their lives, even if the mission succeeds. If you are enjoying this journey, make sure to give this video a like and subscribe. Every video on this channel brings you closer to understanding your place in this vast universe. And trust me, you don't want to miss what's coming next. Now let's talk about psychology, because this might actually be the hardest challenge of all. Humans are social creatures evolved for life in communities, with access to nature, variety, and the freedom to leave difficult situations. An interstellar crew would be trapped in a confined space with the same small group of people for years, unable to leave, unable to call for help, knowing that everyone they've ever known is aging and dying light years behind them. Studies of Antarctic winter over crews, submarine sailors, and long-duration space missions have documented a phenomenon called third quarter syndrome. About 3/4 of the way through a long isolated mission, morale plummets, crew members become irritable, depressed, and conflict-prone. They're past the excitement of the beginning, but not yet close enough to the end to feel hopeful. On a submarine, this lasts weeks. On an Antarctic station, maybe months. On an interstellar voyage, it could persist for years. Interpersonal conflicts in such a confined environment can escalate dangerously. There's nowhere to go to cool off, no neutral third party to mediate, no option to reassign someone to a different post. A personality clash between two crew members could poison the entire mission. Psychological screening would be crucial, but even the most stable, compatible people can develop issues under extreme, prolonged stress. Monotony is another enemy. The same walls, the same faces, the same routine, day after day after day for years. The human brain craves novelty. Deprive it of stimulation, and depression, anxiety, and cognitive decline can result. Interstellar mission planners would need to incorporate variety somehow through virtual reality, extensive libraries of entertainment and educational content, hobbies, creative projects, anything to keep minds engaged. Some proposals even suggest using cryogenic sleep to put crew members into suspended animation for portions of the journey, reducing both psychological strain and resource consumption, though we're nowhere near having that technology ready for humans. And what about the purpose of the mission? If it's a one-way colonization voyage to settle Proxima b, the crew at least has a clear goal and the prospect of a new life. But if it's a scientific flyby or even a round-trip mission, what happens when the crew returns to Earth decades or centuries after they left? Everyone they knew is dead. Their culture has changed beyond recognition. They're strangers in their own homeland, displaced not in space but in time. Some crew members might psychologically break under that knowledge before they even arrive, Let's shift our focus now to what happens when you actually approach Proxima Centauri, because arrival presents a whole new set of challenges that are easy to overlook when you're focused on the journey itself. Remember, unless you've been decelerating for months or years, you're arriving at a significant fraction of light speed. If you're on a flyby mission like the proposed breakthrough Starshot nanocrafts, traveling at 20% the speed of light, you'd zip through the Proxima system in a matter of hours or days at most. From the moment Proxima b fills your field of view until it's behind you, you might have only hours to collect data, take images, measure atmospheric composition if there is an atmosphere, scan for magnetic fields, and transmit everything back to Earth before you vanish into the darkness beyond. And here's a critical point that often gets lost in popular discussions. At 20% light speed, you're moving at roughly 60,000 kilometers per second. Earth orbits the Sun at about 30 kilometers per second. Proxima Centauri b, orbiting its star every 11.2 days, moves at roughly 120 kilometers per second. These velocities matter immensely because they determine what kind of science you can do. Your closing speed with the planet is so high that detailed observation becomes incredibly difficult. Imagine trying to photograph a racing car from another racing car traveling in the opposite direction at highway speeds. Now multiply those speeds by thousands. Your imaging systems need to be extraordinarily fast. Your data processing needs to work in real time, and you have essentially one chance to get it right. There are no second passes. Miss your data collection window, and that's it. The mission fails. This is why deceleration is so important for a meaningful scientific mission, let alone a crude one. You need to slow down, ideally to orbital velocity around Proxima Centauri, so you can study the system properly. But deceleration is just as energy-intensive as acceleration. If you used a laser sail to accelerate, you can't use it to brake unless there's another powerful laser waiting at Proxima to push against your sail in the opposite direction, which there obviously isn't. Some proposals suggest carrying a separate deceleration system. You could pack magnetic sails that deploy and drag against the stellar wind and magnetic field of Proxima. You could carry onboard fuel for a braking burn, though that adds tremendous mass. You could even use gravitational assists from Proxima Centauri or its companion stars Alpha Centauri A and B to shed velocity through carefully planned flybys, though the orbital mechanics of arranging that would be staggeringly complex. Another more exotic idea involves sending two laser sail craft. The first carries extra mass and doesn't slow down. As it passes through the Proxima system, it deploys a mirror. The second craft, following behind, uses its laser sail to reflect light from the departing mirror, effectively braking against it. The physics works in theory, but the precision required, keeping two independently moving spacecraft, a mirror and a sail aligned across millions of kilometers while both are traveling at relativistic speeds, borders on impossible with any technology we can currently envision. Let's assume you solve deceleration and successfully enter orbit around Proxima Centauri. Now you can finally see this alien star system up close. What would you actually observe? Proxima Centauri itself would dominate your sky, but it wouldn't look like the Sun. Red dwarfs emit most of their light in infrared wavelengths. To human eyes, Proxima would appear deep red, almost crimson, casting an eerie, dim light compared to the brilliant yellow-white of our Sun. The star's surface temperature is only about 3,000 degrees Kelvin, compared to the Sun's 5,770 degrees. It's a cool, smouldering ember, but don't let that cool label fool you. Proxima is violent. As a red dwarf, its interior is fully convective, meaning hot plasma churns throughout the entire star, not just in the outer layers like the Sun. This generates powerful, tangled magnetic fields that occasionally snap and reconnect, releasing enormous flares. In 2019, astronomers observed Proxima unleashing a flare that increased its brightness by a factor of 68 over just 10 seconds. The energy released was roughly 10 times greater than the most powerful flares ever recorded from our Sun for any planet orbiting in the habitable zone, which by definition sits close to a dim star like Proxima. These flares are catastrophic. They blast the planet with ultraviolet and X-ray radiation, generate powerful stellar winds, and could strip away atmospheric gases over time. If Proxima b ever had an atmosphere, it might have been eroded away long ago, or perhaps the planet has a strong magnetic field that protects it, like Earth's magnetosphere shields us from solar storms. We don't know yet, but from orbit around Proxima, you'd witness these flares firsthand, dangerous, spectacular eruptions that could threaten your spacecraft's electronics if you're not properly shielded. Now let's turn our attention to Proxima b itself. From your spacecraft's instruments, you'd measure its orbital parameters precisely. Every 11.2 Earth days, it completes one circuit around its star. It's likely tidally locked, meaning one side perpetually faces Proxima while the other faces eternal darkness, just as the Moon always shows the same face to Earth. This creates a bizarre climate scenario. The day side would be scorched by constant starlight and buffeted by stellar flares, while the night side would be frozen in permanent darkness. The only potentially habitable regions might be the terminator zone, the twilight band between eternal day and eternal night, where temperatures could be moderate enough for liquid water. If Proxima b has an atmosphere, and that's a big if, you might detect it through spectroscopy. As the planet passes in front of its star from our perspective, or from your spacecraft's perspective if positioned correctly, starlight filters through the atmosphere. Different molecules absorb specific wavelengths, leaving fingerprints in the spectrum. Oxygen, water vapor, methane, carbon dioxide, each has a signature, detecting biosignature gases. Chemicals that on Earth are produced by life would be one of the most profound discoveries in human history. But here's the hard truth. We probably wouldn't detect anything definitive. The planet is small, the star is dim and noisy with flares, and atmospheric signals are incredibly faint. Even with a spacecraft in orbit, it might take months or years of observations to collect enough data for meaningful analysis. And if the planet has no atmosphere, or only a thin one, or if it's a barren, radiation-scoured rock, well, you've traveled 4.2 light-years to confirm that our nearest potentially habitable world is actually uninhabitable. That's science. Sometimes the answer is disappointing, but it's still an answer, and it would teach us volumes about planetary habitability around red dwarfs, the most common type of star in the galaxy. While you're in the Proxima system, you'd also want to study the star itself. Up-close observations of Proxima's flares, its magnetic field structure, its stellar wind and its long-term variability would revolutionize our understanding of red dwarf physics. You could search for additional planets. Proxima Centauri d, the smaller confirmed planet, orbits even closer to the star than Proxima b, whipping around in just 5 days. There might be other worlds farther out, too cold for life but scientifically fascinating nonetheless. And then there are the Alpha Centauri A and B binary stars, located about 13,000 astronomical units away, roughly 0.2 light-years from Proxima. That's still a vast distance, but it's within reach for a spacecraft already in the system. If your mission design allows, you could spend years exploring not just Proxima, but all 3 stars of the Alpha Centauri system, searching for planets, studying stellar dynamics, and mapping this cosmic neighborhood in detail. But eventually, resources run low, your power systems degrade, components fail, or your mission clock simply runs out. What happens next depends entirely on your mission architecture. If you're on a one-way scientific probe, you transmit your final data packets back to Earth and go silent, drifting forever in interstellar space, or perhaps crashing into a planet or star eventually. If you're a crewed mission, the choices are far more profound. Do you attempt the return journey? That requires another massive energy expenditure to accelerate back toward Earth, followed by deceleration at the other end. A round-trip mission could easily take 30, 40 or 50 years of ship time, and far longer in Earth time depending on relativistic effects. You'd return to an Earth that has moved on, where decades or centuries have passed, where everyone you knew is gone, where history, technology, and society have evolved in ways you can't predict. Or do you stay? If Proxima b or another body in the system can support human life, even marginally, perhaps the crew decides to become colonists, the first humans to settle another star system. It's a one-way decision, burning all bridges. But it means your descendants, if you have any, become citizens of a new world, shaped by a red sun instead of a yellow one, with stories of Earth as a distant legend. There's something deeply moving about that idea, isn't there? Humans, evolved on the plains of Africa, shaped by 4 billion years of earthly evolution, stepping onto a world that has never known life, planting a flag, building a habitat and saying, "This is home now." We carry Earth with us in our biology, our culture, our memories, but we'd also be transformed by the new environment, beginning a divergence that over thousands of generations might lead to a new branch of humanity adapted to a red dwarf's light and a different gravity and a different sky. But let's ground ourselves again in the reality of what colonization would actually entail, because science fiction often glosses over the brutal practicalities. Establishing a permanent human presence on Proxima b, or any world in that system, would be orders of magnitude harder than anything humanity has ever attempted. Consider what colonists would need to survive: air, water, food, shelter, energy, and protection from radiation. On Earth, nature provides most of these for free. On Proxima b, you're starting from nothing. If the planet has an atmosphere, is it breathable? Almost certainly not. You'd need sealed habitats with life support systems, essentially carrying a piece of Earth's biosphere with you. If the planet has water ice or subsurface water, you could extract and purify it, but that requires energy and equipment. If not, you're entirely dependent on recycling. With zero margin for error, growing food becomes critical for long-term survival. You can't rely on supply ships from Earth when each one-way journey takes years or decades, but agriculture on an alien world faces challenges we've barely begun to understand. Proxima's light spectrum is weighted toward red and infrared. Earth plants evolved under the sun's spectrum. Would they photosynthesize efficiently under Proxima's light? Some experiments suggest plants can adapt, but yields might be lower, growth slower. You'd need supplemental lighting, which means more energy demand. Then there's soil. Proxima b doesn't have soil, not in the earthly sense. Soil is a living ecosystem, filled with microorganisms, fungi, and organic matter built up over millions of years. You'd need to bring soil microbes from Earth or create artificial growing media. And you'd have to protect your crops from whatever environmental hazards exist, whether that's radiation, temperature extremes, or unknown chemical composition in the regolith. Energy is perhaps the most fundamental need. On Earth, we harness solar, wind, hydro, fossil fuels, and nuclear power. On Proxima b, your options are limited. Solar panels would work, though the lower light intensity means you'd need larger arrays for the same power output. Wind energy requires an atmosphere with weather patterns, hydro requires flowing water, fossil fuels obviously don't exist. That leaves nuclear as your most reliable option. You'd need to bring fission reactors, fuel, and the engineering expertise to maintain them, possibly for generations. And then there's the psychological weight of colonization. The first colonists would know, with absolute certainty, that they will never see Earth again. No video call can overcome 4.24-year communication delays. No rescue mission will arrive if things go catastrophically wrong. You're pioneering in the truest, most isolated sense imaginable. The mental resilience required for that, especially across multiple generations born on Proxima b, who will only know Earth through stories and recordings, is something we can barely comprehend. Children born on Proxima b would be alien in ways their parents aren't. If the gravity is different, their bones and muscles would develop differently. Their circadian rhythms might adapt to the planet's rotation, which could be very different from Earth's 24-hour day. They'd grow up under a red sun, never seeing a blue sky unless through photographs. Earth would be a myth to them, a place their ancestors came from, as distant and unreal as ancient Mesopotamia is to us. Over generations, isolated from Earth's gene pool, genetic drift would occur, mutations would accumulate. If the colony is small, inbreeding could become a problem unless carefully managed. Over thousands of years, Proxima colonists might diverge enough from Earth humans to be considered a separate subspecies. We'd be witnessing speciation, not of animals or plants, but of ourselves. It's a profound, even unsettling thought. Now let's zoom out and consider the bigger picture. Why go to Proxima Centauri at all? What drives this desire to cross such impossible distances, to endure such hardship and risk? Part of it is survival. Earth is fragile. Asteroid impacts, supervolcano eruptions, climate change, nuclear war, pandemics, these are real existential risks. Having a backup location for humanity, even one as remote as Proxima's Manta B, improves our species' long-term survival odds. As the physicist and author Stephen Hawking often argued, becoming a multi-planet species is essential to ensuring humanity's future. Keeping all our eggs in one planetary basket is dangerous. But there's more to it than survival. It's about curiosity, that fundamental human drive to explore, to see what's beyond the next hill, the next ocean, the next star. For most of human history, there was always somewhere new to explore on Earth. But now we've mapped every continent, climbed every major mountain, plumbed the deepest oceans. The only frontiers left are space and the mysteries of fundamental science. Interstellar travel represents the ultimate frontier, the final outward journey. It's also about perspective. Every time humanity has expanded its horizons, whether through the voyages of Polynesian navigators, the Silk Road traders, the Age of Exploration, or the Space Age, we've gained not just new resources or territory, but new understanding. We've learned about ourselves, our place in the world, the diversity of life and culture. Reaching another star system would be the grandest expansion yet, forcing us to confront what it means to be human when Earth is just a memory, and there's the scientific imperative. We've learned an astonishing amount about the universe from here on Earth, and from our spacecraft exploring the solar system. But imagine what we'd learn from direct, up-close study of another star and its planets. Imagine analyzing rocks from Proxima b in a laboratory. Imagine measuring the stellar wind of a red dwarf from within its habitable zone. Imagine discovering microbial life, even fossil life, proving that biology is not unique to Earth. Those discoveries would reshape our understanding of life, the universe, and our place within it. Let's talk more about the search for life, because that's really one of the central questions that would drive a mission to Proxima Centauri. Is there life on Proxima b? Could there be life? The conditions for life as we know it are fairly specific. You need liquid water, organic molecules, an energy source, and enough time for chemistry to become biology. Earth had all of these, and life emerged remarkably quickly. Within the first few 100 million years after the planet cooled enough to have liquid oceans, that suggests that life might not be terribly difficult to start, given the right conditions. But Proxima b faces challenges Earth didn't. The stellar flares we talked about earlier are a major problem. High-energy radiation breaks apart complex molecules and damages DNA, or its alien equivalent. Life on Earth is protected by our atmosphere and magnetic field. If Proxima b lacks those protections, the surface might be sterilized, bathed in radiation during every major flare. However, life is remarkably tenacious. On Earth, extremophiles thrive in boiling hot springs, frozen Antarctic lakes, deep underground, and even in the cooling water of nuclear reactors. If life exists on Proxima b, it might be sheltered underground, in caves or beneath ice, protected from surface radiation. Or perhaps it evolved different biochemical strategies to repair radiation damage more efficiently than Earth life. There's also the question of tidal locking. If one side of Proxima b always faces the star, you might get atmospheric circulation patterns that transport heat from the day side to the night side, creating a habitable zone in between. Or the atmosphere might freeze out on the night side and the planet becomes uninhabitable. Climate models give different answers depending on assumptions about the planet's atmosphere, rotation, and ocean coverage. We simply don't know yet. If your spacecraft detects even a hint of biological activity, whether it's spectroscopic signatures of oxygen and methane in disequilibrium, surface features that suggest seasonal changes, or chemical anomalies in the atmosphere, that would be one of the most important discoveries in human history. It would confirm that life is not unique to Earth, that the universe is teeming with biology, that we are not alone. But let's consider the opposite scenario, the one that might actually be more likely. What if Proxima b is dead? What if your spacecraft arrives after years of journey and all the measurements, all the spectroscopy, all the surface scans reveal nothing but barren rock, thin or no atmosphere, no water, no chemistry that even hints at biology? What if the nearest potentially habitable world turns out to be completely sterile? That would be a profound discovery in its own way. It would tell us that habitability is rarer and more fragile than we hoped. It would suggest that the specific conditions Earth enjoys, our distance from a stable, long-lived G-type star, our large moon stabilizing our axial tilt, our magnetic field protecting us from stellar wind, our plate tectonics recycling minerals and regulating climate, all of these might be more critical than we thought. The universe might be filled with planets, but worlds that actually support life could be vanishingly rare. This is the heart of the Fermi paradox, the troubling question of why, if the universe is so vast and old, we see no evidence of other civilizations. Where is everybody? One answer is that life itself, or at least complex technological life, might be extraordinarily rare. Perhaps Earth is a cosmic fluke, and we're alone in the galaxy, possibly even in the observable universe. Finding Proxima b lifeless would push us slightly more toward that sobering conclusion. Or perhaps life is common, but intelligence is rare. Earth has hosted life for roughly 3.7 billion years, but technological civilization emerged only in the last few thousand years, a blink of an eye in geological time. For most of Earth's history, life was microbial. Complex multicellular organisms only appeared about 600 million years ago. Intelligence took even longer. Maybe the galaxy is full of microbial life, slime and bacteria on countless worlds, but we're the only ones who built telescopes and radio transmitters. There's another, darker possibility. Maybe civilizations do arise frequently, but they don't last long. They destroy themselves through war, environmental collapse, or resource depletion before they can spread to the stars. We're currently facing that test ourselves with climate change, nuclear weapons, and artificial intelligence risks. Perhaps every civilization reaches a critical threshold where their technology becomes powerful enough to destroy them, and most fail that test. The galaxy might be littered with the ruins of civilizations that never made it to the stars. Reaching Proxima Centauri would be humanity, proving we passed that test, at least long enough to achieve something monumental. It would demonstrate that we controlled our self-destructive impulses long enough, cooperated on a global scale effectively enough, and maintained focus across generations sufficiently to accomplish something that required centuries of dedication. That in itself would be a triumph. Let's talk about timescales, because this is where interstellar travel really challenges our psychology and our social structures. Most human endeavors operate on short timescales. Political terms last a few years. Business quarters are 3 months. Even major construction projects, building cathedrals or pyramids or dams, typically span decades at most. But an interstellar mission would require thinking in terms of generations. Consider a realistic mission architecture using near-term technology. Chemical rockets won't cut it, they're far too slow. Nuclear propulsion could potentially accelerate a spacecraft to maybe 5 to 10% the speed of light after years of continuous thrust. At 5% light speed, the journey to Proxima Centauri takes 85 years. Add time for acceleration and deceleration, and you're looking at a century or more. No one who designs and builds that spacecraft will live to see it arrive. The engineers, scientists, and political leaders who initiate the project will be long dead. The astronauts who launch might survive the journey in cryogenic sleep if we develop that technology, or they might be a multi-generational crew with children and grandchildren born en route. By the time the mission sends back data from Proxima, another 4.2 years pass for the signal to reach Earth. The people who receive that data might be the great-great-grandchildren of the people who launched the mission. Can our civilization maintain focus and commitment across such timescales? Human history suggests it's difficult. Political priorities shift, economic conditions change, wars erupt, technologies become obsolete. The Apollo program put humans on the moon, but then we stopped going. It's been over 50 years since the last Apollo mission, and we still haven't returned. Public interest waned, budgets got redirected, priorities changed. An interstellar mission would require sustained commitment orders of magnitude longer than Apollo. One model is the way some institutions do operate across long timescales. Universities have existed for centuries, religious institutions for millennia. Some scientific projects, like monitoring astronomical objects or maintaining seed banks, are designed to last generations. Perhaps an interstellar mission would need to be framed not as a government program subject to political whims, but as a civilizational project embedded in our culture, maintained by international collaboration, with built-in redundancy so that even if one nation loses interest, others continue the work. There's also the economic question. How much would an interstellar mission cost? It's almost impossible to estimate because we don't know what technology we'd use, but we can make some educated guesses. The Apollo program cost about $130 billion in today's money over a decade. The International Space Station has cost over $150 billion over its lifetime. An interstellar mission would be vastly more expensive, likely trillions spread across decades or centuries. Is that affordable? The global economy is roughly $100 trillion annually. If humanity collectively devoted even 0.1% of global GDP to an interstellar mission, that's $100 billion per year. Over a century, that's $10 trillion, likely enough to develop the necessary technologies and launch a mission. It would be the largest cooperative project in human history, but not impossibly expensive if framed in global terms. The harder question is political will. Why spend trillions on space when there are urgent problems on Earth, poverty, disease, climate change, inequality? It's a legitimate question, and there's no easy answer. Some argue that space exploration inspires innovation that benefits everyone, that technologies developed for space have terrestrial applications, and that striving for great goals unites humanity. Others counter that we should solve Earth's problems first before we worry about other stars. My own view is that it's not an either-or proposition. We can address problems on Earth and pursue space exploration simultaneously. In fact, the long-term survival challenges we face on Earth, energy, resources, sustainability, require exactly the kind of ambitious, forward-thinking engineering and science that space exploration demands. The technologies we develop for interstellar travel, closed-loop life support, advanced propulsion, autonomous robotics, extreme efficiency would have enormous benefits here at home. And there's an inspirational element we shouldn't dismiss. Humanity needs goals that transcend daily politics and national borders. The moon landings inspired an entire generation to pursue science and engineering. An interstellar mission could do the same, but on a scale that unites the entire planet. When your project timeline spans centuries, petty national rivalries seem absurd. You're thinking as a species, not as competing tribes. Let's consider what an interstellar mission would mean for human unity. Right now, we're divided by nations, religions, ideologies, and economic systems, but an interstellar mission would require unprecedented cooperation. No single nation could do it alone. You'd need resources, expertise, and infrastructure from across the planet. The spacecraft would carry representatives of humanity as a whole, not just one country. Imagine the symbolism of that. A crew chosen from diverse nations, cultures, and backgrounds, carrying with them the collective knowledge and hopes of Earth. They'd be ambassadors not to alien civilizations, we don't know if those exist, but ambassadors from humanity to the cosmos itself. What they discover for all of us. When they succeed or fail, we all share in that outcome. There's also the question of what message we send with such a mission, literal and figurative. Pioneer and Voyager carried plaques and golden records with images, sounds, and information about Earth, designed for any hypothetical alien intelligence that might find them. An interstellar mission to Proxima would likely carry something similar, an archive of human culture, history, art, and science. What would you include? Music from Bach, Beatles, and traditional songs from around the world, images of Earth's diversity, landscapes, wildlife, people, explanations of our mathematics, physics, and biology, personal messages from ordinary people. It's a profound exercise in selecting what represents humanity at our best, and it forces us to ask, what do we want to say about ourselves to the universe, or to our descendants who might find these records thousands of years from now? There's also a haunting possibility we should address. What if we launch an interstellar mission, and then decades later, we develop faster technology? Imagine this scenario. In 2100, humanity launches a spacecraft using the best available technology, capable of reaching Proxima Centauri in 80 years. But then in 2150, we achieve a breakthrough in propulsion, maybe practical fusion drives or even something more exotic, and we launch a second spacecraft that can make the journey in just 20 years. The second spacecraft arrives decades before the first one. This is called the weight equation, or interstellar weight problem. It raises an uncomfortable question. Should you ever launch an interstellar mission, knowing that waiting a bit longer might produce technology that makes your current mission obsolete? If you launch too early, you waste resources on a slower mission. But if you always wait for better technology, you never launch at all because there's always something better on the horizon. The resolution, I think, is that at some point you have to commit. You assess your technology, accept that it's good enough, and go forward knowing that future generations might surpass you. And honestly, having multiple missions at different speeds might not be a bad thing. The earlier, slower spacecraft become pioneers, the first to arrive, while later missions bring more advanced equipment and can build on the earlier discoveries. It's redundancy, and redundancy is good for such high-stakes ventures. Now let's talk about some of the more speculative, far-future technologies that could potentially make interstellar travel not just possible, but almost routine. Because if we're being honest, everything we've discussed so far, laser sails, fusion drives, generation ships, these are barely feasible with decades or centuries of development. But if we're thinking on timescales of thousands of years, what might become possible? Antimatter propulsion is one option. When matter and antimatter meet, they annihilate completely, converting mass directly into energy with 100% efficiency according to Einstein's E=mc². No other energy source even comes close. A antimatter-matter reaction releases roughly 10 billion times more energy per kilogram than chemical reactions, and about 100 times more than nuclear fusion. The problem is producing and storing antimatter. Right now, we can create tiny amounts in particle accelerators, but it takes vastly more energy to produce antimatter than you get back from it. You'd need enormous facilities in space, powered by gigantic solar arrays or fusion reactors dedicated to antimatter production. Then you'd need to store it, and antimatter annihilates instantly if it touches normal matter. So you need magnetic bottles or other containment systems that never fail. A single containment breach, and your entire fuel supply explodes with the force of multiple nuclear weapons. Despite these challenges, antimatter propulsion could theoretically accelerate a spacecraft to a significant fraction of light speed, maybe 20 to 50%, making the journey to Proxima Centauri feasible in decades rather than centuries. It's a technology that might be achievable in a few centuries if we dedicate ourselves to it. Then there are even more exotic possibilities. Warp drives inspired by science fiction but grounded in actual physics, specifically the Alcubierre metric proposed by physicist Miguel Alcubierre in 1994. The idea is to contract space in front of your spacecraft and expand it behind you, creating a warp bubble that moves through space faster than light, while the spacecraft inside remains stationary relative to the bubble. You're not technically moving faster than light through space. Space itself is moving around you. The physics technically works according to general relativity, but it requires exotic matter with negative energy density, something we've never observed and don't know how to create. The energy requirements are astronomical, potentially requiring the mass energy of entire planets or even stars. More recent refinements have reduced the theoretical energy requirements, but we're still talking about energy scales far beyond anything we can currently manipulate. Would warp drives ever be practical? Maybe. Arthur C. Clarke famously said that any sufficiently advanced technology is indistinguishable from magic. To someone from the 19th century, smartphones, GPS, and jet aircraft would seem like magic. Perhaps a civilization thousands or millions of years more advanced than ours would find warp drives as routine as we find jet engines, or perhaps the laws of physics truly forbid it, and faster-than-light travel is impossible, no matter how clever you are. We don't know yet. There's also the concept of wormholes, tunnels through space-time connecting distant locations. If you could create or find a wormhole with one mouth near Earth and the other near Proxima Centauri, you could step through and travel 4.2 light-years in an instant. Again, this is theoretically possible in general relativity, but it requires exotic matter to keep the wormhole open, and we have no idea how to create one. It's firmly in the realm of speculation, something to inspire science fiction, but not something engineers are working on. More realistic in the nearer term is the idea of suspended animation or cryogenic sleep. If we could safely freeze human beings or put them in a state of extremely slowed metabolism, crew members could sleep through most of the journey, aging only a few years while decades or centuries pass. This would solve many of the psychological and resource challenges of long-duration spaceflight. Nature actually provides some models for this. Some organisms, like tardigrades and certain frogs, can enter states of cryptobiosis where their metabolism essentially stops. They can survive freezing, desiccation, radiation, and vacuum, then revive when conditions improve. Some mammals hibernate, slowing their metabolism dramatically for months at a time. If we could understand and replicate these mechanisms for humans, long-duration spaceflight becomes much more feasible. Current research in this area is promising but still early stage. We can freeze and successfully revive small organisms, certain tissues, even some organs for short periods. Human embryos are routinely frozen and later used for in vitro fertilization. But freezing a whole adult human without causing catastrophic ice crystal damage to cells, then reviving them months or years later. We're not there yet, but it might be achievable with enough research. Another approach is pharmacological suspended animation, using drugs to slow metabolism rather than freezing. Some research has successfully induced hibernation-like states in animals that don't normally hibernate. This might be safer than freezing and more easily reversible. Imagine crew members taking a medication that slows their heart rate to a few beats per minute, drops their body temperature, and reduces their caloric needs to almost nothing. They sleep in climate-controlled pods for decades, monitored by automated systems, waking periodically for health checks before returning to sleep. If suspended animation works, you could launch a spacecraft with a small crew who sleep most of the journey, waking only when they approach Proxima Centauri. The psychological burden is eliminated. Resource requirements drop dramatically. The spacecraft can be smaller and lighter because you don't need living space for active crew, just efficient sleep pods. It's not faster than light travel, but it makes slow travel psychologically tolerable. Let's shift gears and talk about artificial intelligence, because AI might be the real key to interstellar exploration. Human space travel is hard because humans are fragile. We need air, water, food, radiation shielding, gravity or exercise to prevent muscle loss, psychological stimulation, and more. We're biological machines optimized for Earth's environment, not the void of space. Robots and AI have none of these limitations. They don't need air or food. They can be shielded much more easily against radiation. They don't get bored or lonely. They can be shut down for years and reactivated without aging. An AI-controlled spacecraft could be smaller, lighter, faster, and far more reliable than a crewed mission. The Voyager probes, launched in 1977, are still functioning nearly 50 years later, billions of miles from Earth. They're primitive by modern standards, with computers less powerful than a smartphone, yet they continue to send back data from interstellar space. Imagine what we could do with modern AI machine learning systems that can adapt to unexpected conditions, diagnose and repair problems autonomously, and make intelligent decisions without waiting years for instructions from Earth. An AI-driven interstellar probe could conduct sophisticated science at Proxima Centauri, analyzing atmospheric composition, studying the star's magnetic field, mapping planetary surfaces, even deploying smaller probes to land and collect samples, all without human guidance, because by the time radio signals travel 4.2 light-years each way, the window for meaningful real-time control is gone. There's an even more radical idea: von Neumann probes, self-replicating spacecraft named after mathematician John von Neumann, who studied self-replicating systems. The concept is simple yet profound. You send a spacecraft to another star system equipped with AI and manufacturing capabilities. When it arrives, it uses local resources, asteroids, comets, planetary materials, to build copies of itself. Those copies then travel to other star systems and repeat the process. With exponential replication, a single von Neumann probe could theoretically explore the entire galaxy in a few million years, a blink of an eye in cosmic terms. Each probe gathers data and transmits it back to Earth or to a growing network of probes. You'd create a vast intelligence-gathering network spanning the galaxy, all originating from a single initial spacecraft. The technical challenges are immense. You need AI sophisticated enough to locate resources, design and operate mining and manufacturing equipment, troubleshoot problems, and avoid self-destructive errors. You need manufacturing systems compact enough to fit on a spacecraft, yet versatile enough to build complex components. You need to prevent mutation or corruption in the replication process. Otherwise, the probes might evolve into something other than their intended purpose. There are also ethical and safety concerns. A self-replicating system that gets out of control could become a grey goo scenario, consuming resources indiscriminately and spreading uncontrollably. If we send von Neumann probes into the galaxy, are we obligated to ensure they don't damage any ecosystems they encounter? What if a probe arrives at a planet with primitive life, or even intelligent life? Does it have ethical constraints programmed in? Who decides what those constraints are? These questions might seem premature when we haven't even sent a simple probe to another star yet, but they're worth thinking about now. The decisions we make about the design and purpose of interstellar probes could have consequences echoing across the galaxy for millions of years. That's not hyperbole. If we create self-replicating probes, they might still be functioning long after human civilization as we know it has transformed into something unrecognizable or even ceased to exist. This brings up one of the most fascinating and unsettling aspects of interstellar exploration: deep time. We're used to thinking in terms of human lifespans, maybe a century. Civilizations rise and fall over centuries or millennia. But the universe operates on timescales of billions of years. Stars live for millions or billions of years. Galaxies evolve over billions of years. When you send a spacecraft to another star, you're participating in processes that unfold over cosmic time. Proxima Centauri itself is a red dwarf, and red dwarfs are the longest-lived stars in the universe. Proxima will continue burning for trillions of years, long after our sun has died, long after all the massive bright stars have exhausted their fuel and gone supernova or collapsed into black holes. In the far future, when the universe is old and most stars have burned out, red dwarfs like Proxima will be among the last lights in the cosmos. Any civilization or probe we establish there could potentially persist for unimaginable spans of time. That's a profound legacy. Whatever we send to Proxima Centauri might outlast not just us, but our entire species, possibly even our planet. If we encode knowledge about humanity, our culture, our science, our history, that information could survive for billions of years. Long after Earth is gone, absorbed by the Sun in its red giant phase 5 billion years from now, a probe orbiting Proxima Centauri could still be there, a message in a bottle from a long-extinct civilization, waiting for someone to find it. Or perhaps by then, humanity will have spread across the galaxy and will still be around, unimaginably transformed by evolution, technology, or merging with AI, but continuous in some way with the species that built that first probe. Our descendants might look back at that initial mission to Proxima the way we look back at the first humans who walked out of Africa, a crucial step in a journey of expansion that never really ended. Let's talk about the cultural impact of interstellar exploration, because this isn't just about science and engineering. An interstellar mission would profoundly affect human culture, philosophy, and self-perception. First, it would be a unifying project. I mentioned this earlier, but it's worth emphasizing. National borders, ethnic divisions, religious differences, these seem absurdly petty when you're contemplating the distances between stars. An interstellar mission would require global cooperation on an unprecedented scale. It would force us to think of ourselves as one species, one civilization, with a common goal and shared destiny. That shift in perspective could be transformative. We've seen glimpses of this before. The famous blue marble photograph of Earth taken by Apollo 17, showing our planet as a small, fragile sphere against the blackness of space, had a profound impact on environmental awareness and the sense of Earth as a single, interconnected system. The pale blue dot image captured by Voyager 1 from the edge of the solar system, showing Earth as a tiny pixel, inspired Carl Sagan's famous reflection on our place in the cosmos. An interstellar mission would amplify that perspective 1,000-fold. When your spacecraft is light years away, looking back at Earth, our planet becomes not just small but invisible, lost in the glare of the sun, indistinguishable from countless other stars. That perspective, that cosmic humility, could reshape how we think about our conflicts and priorities. There's also the effect on culture and art. Exploration has always inspired storytelling, mythology, and artistic expression. The age of exploration produced countless works of literature, from travelogues to epic poems. The space age inspired a golden age of science fiction, visionary films, and music. An interstellar mission would inspire artists, writers, musicians, and filmmakers for generations. Imagine the stories told by people who lived through the launch, watching the spacecraft depart, knowing they'd never see it arrive. Imagine the songs written about the astronauts sleeping through decades, crossing the void between stars. Imagine the films depicting the first images received from Proxima Centauri, the moment when humanity sees another world close up for the first time. These cultural artifacts would become part of our shared heritage, stories told and retold, defining what it means to be human in the interstellar age. And there would be philosophical implications. Religion and philosophy have long grappled with questions of humanity's place in the universe, our purpose, our significance. Interstellar travel doesn't answer those questions, but it reframes them in stark terms. Are we alone? If we find life, even microbial life on Proxima b, it suggests that life is common in the universe. The implications for theology, philosophy, and our self-perception would be enormous. If life arises readily wherever conditions allow, then perhaps the universe is teeming with biology, and we're just one instance among countless others. That's humbling but also comforting. We're part of a universal process, not a cosmic fluke. But if we find nothing, if Proxima b and other worlds we can reach are barren, then perhaps life is extraordinarily rare, and we might be alone in our galaxy, maybe even beyond. That places enormous responsibility on us. We become the custodians of life itself, the only consciousness capable of understanding and appreciating the universe. If we fail, if we go extinct before spreading to other worlds, we extinguish not just one species, but perhaps the only light of consciousness in a vast, dark cosmos. These aren't just abstract philosophical musings. They affect how we value ourselves and our planet, how we approach existential risks, and what priorities we set as a civilization. If we believe we're part of a universe filled with life, we might approach space differently than if we believe we're utterly alone. Both perspectives call for exploration, but for different reasons. Let's consider some of the practical spin-off benefits of developing interstellar travel technology, because often the journey produces as much value as the destination. When President Kennedy announced the goal of landing on the moon, he wasn't just interested in lunar rocks. He wanted to drive technological innovation, inspire the nation, and demonstrate American capability. The Apollo program delivered all of that, plus massive technological spin-offs. Technologies developed for Apollo gave us integrated circuits, computer miniaturization, advanced materials, fuel cells, water purification systems, and satellite technology. These innovations revolutionized computing, communications, medicine, and countless other fields. The economic return on investment from Apollo has been estimated at $7 to $14 for every dollar spent just from the technological spin-offs, not even counting the scientific knowledge gained. An interstellar mission would require advances across dozens of fields. Propulsion systems developed for interstellar travel could revolutionize satellite deployment and deep space exploration. Life support systems designed for century-long missions could improve sustainability technology on Earth, creating closed-loop systems that recycle everything with perfect efficiency. Advanced AI and robotics developed for autonomous spacecraft could transform manufacturing, medicine, and exploration here at home. Materials science would advance dramatically. You need materials that can withstand decades or centuries in space without degrading, that can handle extreme temperatures, radiation, and micrometeorite impacts. Those materials would have applications in everything from infrastructure to consumer products. Energy technology would leap forward. Whether you develop fusion drives, antimatter propulsion, or massive laser arrays, those energy technologies would transform power generation on Earth. Fusion power would provide clean, virtually limitless energy. Advanced solar power systems would make renewable energy far more efficient. These alone could be worth the entire investment. Communication technology would advance to handle the challenges of interstellar distances, error correction, data compression, and signal processing for messages traveling light years would push the boundaries of information theory. Those advances would improve all communications on Earth and throughout the solar system. Medical technology would benefit enormously. Research into suspended animation, radiation protection, and long-term health in space would advance our understanding of human biology. Technologies to prevent muscle and bone loss in zero gravity could help elderly people on Earth. Understanding how to protect against radiation could improve cancer treatment. The closed-loop systems for recycling biological waste could advance understanding of metabolism and nutrition, and perhaps most importantly, education and inspiration. The Apollo program inspired an entire generation to pursue careers in science, technology, engineering, and mathematics. The spike in STEM graduates in the 1970s and 80s can be traced directly to Apollo's influence. Those scientists and engineers went on to create the personal computer revolution, the internet, biotechnology, and countless other innovations that define modern life. An interstellar mission would inspire on an even grander scale. Children growing up during the development and launch of an interstellar spacecraft would dream of being the scientists, engineers, and astronauts who make such things possible. That inspiration would drive educational achievement, scientific curiosity, and technological innovation for decades. The long-term economic and social value of that inspiration is incalculable, but undoubtedly enormous. Now let's address some of the legitimate criticisms and concerns about interstellar exploration, because it's important to think through the counter-arguments. The most common objection is cost and priorities. Why spend trillions on space when people are hungry, sick, and suffering on Earth? Shouldn't we solve our problems at home before we worry about other stars? It's a valid concern, and it deserves a serious answer. First, the choice isn't binary. We can address poverty, disease, and inequality while also pursuing space exploration. The global economy is enormous, over $100 trillion annually. The amount needed for an interstellar mission, while large in absolute terms, is small relative to global spending. We spend more on cosmetics, more on military weapons, more on countless things that provide less lasting value than an interstellar mission. Second, many of Earth's problems aren't primarily resource problems, they're political, social, and organizational problems. Hunger persists not because we lack food, we produce enough to feed everyone, but because of distribution failures, conflict, and political dysfunction. Spending more money doesn't automatically solve these issues. In fact, the global cooperation required for an interstellar mission might help us develop the the diplomatic and organizational capabilities to address Earth's problems more effectively. Third, as I mentioned, the technological spin-offs from space exploration often have enormous benefits for addressing Earth's problems. Satellite technology enables weather forecasting that saves lives, GPS that improves agriculture and logistics, communications that connect remote regions. Medical technology developed for space has improved healthcare. Materials science advances have improved countless products. The investment in space technology pays dividends in unexpected ways. Fourth, there's value in aspirational goals that transcend daily concerns. Humans need meaning, purpose, and inspiration. Great projects like cathedrals, monuments, or space missions give people a sense of participating in something larger than themselves. That psychological and cultural value is real, even if it's hard to quantify in economic terms. But let's be honest, there's also an element of pure exploration for its own sake, the desire to know what's out there, to push boundaries, to achieve difficult things because they're difficult. That impulse has driven human progress throughout history. The first humans who crossed oceans, climbed mountains, or explored polar regions often had no practical justification. They did it because it was there, because they could, because some deep human instinct drives us to explore. That instinct has served our species well, leading to discoveries and expansions that have enriched all of humanity. Another criticism is environmental concern. Should we spread beyond Earth when we've done such damage to our own planet? Do we have the right to potentially contaminate other worlds with Earth life or to exploit their resources? This is a serious ethical question that deserves careful consideration. There's a principle in planetary science called planetary protection, the idea that we should avoid contaminating other worlds with Earth life and avoid contaminating Earth with potentially harmful extraterrestrial material. For missions to Mars and other places where life might exist, we sterilize spacecraft to minimize the risk of contamination. An interstellar mission would need similar or even stricter protocols. If Proxima b has life, we'd need to be extremely careful. Even if it's just bacteria, introducing Earth microbes could disrupt or destroy the native ecosystem. It would be an irreversible loss of unique biology and knowledge. On the other hand, if Proxima b is sterile, is there an ethical problem with humans or our technology going there? If no life exists, what's harmed by our presence? Some argue for a preservationist ethic, leave everything untouched, even dead worlds, out of respect or caution. Others argue for an expansionist ethic. It's acceptable or even good to spread life, intelligence, and civilization to currently lifeless worlds, enriching the universe rather than leaving it barren. There's no consensus, and perhaps there can't be until we know more about how common or rare life actually is. My own inclination is toward caution and respect. If we find life, even microbial life, we should study it carefully and minimize our impact. If we find sterile worlds, we might consider establishing presences there, but thoughtfully and with long-term sustainability in mind, not exploitative strip mining. The decisions we make set precedents for how humanity behaves in the cosmos for thousands or millions of years to come. We should make those decisions carefully and humbly. There's also a practical concern about feasibility. Are we really capable of building and launching an interstellar mission? The technical challenges are enormous, far beyond anything we've attempted. The Apollo program pushed the limits of 1960s technology and succeeded, but it had clear technical pathways and only required a decade of focused effort. An interstellar mission might require technologies we don't yet have and can't yet imagine. Is it realistic to think we can do this? I think the answer is yes, but not quickly and not easily. We won't launch an interstellar mission next decade or even next century with current technology. But over the course of centuries, as our technology continues to advance, as we establish a robust presence in our own solar system, as we develop better propulsion, better AI, better materials, an interstellar mission becomes increasingly feasible. The key is maintaining long-term commitment and making steady progress. We build space stations and learn to live in space for extended periods. We establish bases on the Moon and Mars and learn to use local resources. We develop asteroid mining and space manufacturing. We build larger and more capable spacecraft. We push our propulsion technology forward, from chemical to ion to nuclear to fusion to whatever comes next. Each step makes the next step more achievable. Think of it like building a cathedral in medieval times. No single generation could complete it. The people who laid the foundation knew they'd never see the finished building, but they did their part, knowing their children and grandchildren would continue the work. Over centuries, the cathedral was completed. An interstellar mission might work the same way. We lay the foundations now, developing the basic technologies and building the infrastructure. Future generations continue the work, improving and expanding what we started. Eventually, perhaps centuries from now, the mission launches. That requires a shift in how we think about large projects. We're used to seeing results within our lifetimes, ideally within a few years. An interstellar mission requires thinking across generations, accepting that we might contribute to something we'll never see completed. That's psychologically difficult, but it's also noble. It means working for the benefit of future generations, not just ourselves. It means being part of a story larger than our individual lives. Let me share a personal reflection here. When I think about interstellar exploration, I feel a complex mix of emotions. There's excitement at the possibilities, the potential discoveries, the triumph of human capability. There's awe at the scales involved, the distances, the energies, the time frames. There's humility at recognizing how small we are against the backdrop of the cosmos. But there's also a kind of melancholy. The stars are so far away. Even our nearest neighbor is separated from us by a gulf that challenges our very ability to cross it. We look up at the night sky and see thousands of stars, and we know each of those is a sun, potentially with planets, maybe with life, possibly with civilizations. But they're so distant that we may never reach them, never know what's there, never make contact. If you are still watching, please subscribe to the channel. Your support is the biggest fuel to keep this channel going. The physicist Enrico Fermi famously asked, "Where is everybody?" If the universe is so vast, with billions of galaxies, each containing billions of stars, many with planets, some surely with life, then where are all the aliens? Why haven't we detected any signals, any probes, any evidence of other civilizations? This is the Fermi paradox, and it's one of the most profound questions in science. There are many proposed solutions. Maybe life is extremely rare, and we're alone or nearly alone. Maybe intelligent life emerges but quickly goes extinct before achieving interstellar travel. Maybe advanced civilizations exist but stay quiet, avoiding detection for reasons we don't understand. Maybe they're out there but so different from us that we don't recognize their signals or technology. Maybe the distances are simply too vast, and civilizations are islands of intelligence separated by oceans of space and time, never managing to make contact before they fade away. Or maybe, and this is the hopeful thought, maybe we're early. The universe is 13.8 billion years old, but most stars will live for trillions of years. Perhaps we're among the first civilizations to emerge, part of the first wave of intelligence in a cosmos that will eventually teem with life. If so, what we do matters enormously. The choices we make, the paths we follow, might set templates that other civilizations learn from or repeat. We might be cosmic pioneers, not knowing it, doing things for the first time that will be done countless times in the eons to come. An interstellar mission to Proxima Centauri would be one small step in becoming that kind of civilization. It wouldn't answer all questions or solve all problems, but it would demonstrate that humans can think beyond ourselves, beyond our planet, beyond our solar system. It would show that we can accomplish things that require generations of effort. It would expand the sphere of human experience and knowledge to another star system, and perhaps, just perhaps, it would be the beginning of something much larger. If we can reach Proxima, we can eventually reach other nearby stars. Alpha Centauri A and B are part of the same system, only slightly farther. Barnard's star, Wolf 359, Lalande 211185. These are all within 10 light-years, challenging but potentially reachable with similar technology. Step by step, star by star, we could extend our reach, creating a network of outposts, probes, maybe even colonies throughout our local stellar neighborhood. Over thousands of years, that expansion could continue. Over millions of years, we or our descendants, biological, technological, or some fusion of both, could spread across the galaxy. The Milky Way contains 200 to 400 billion stars. If we reached just a tiny fraction of them, we'd still be talking about billions of star systems explored, understood, maybe inhabited. It's an almost unimaginable vision, but then again, so would our current civilization be unimaginable to humans 10,000 years ago. They lived in small tribes, hunting and gathering, with no writing, no cities, no technology beyond stone tools and fire. If you could show them images of modern cities, aircraft, computers, spacecraft, they'd think it was magic or the work of gods. Yet here we are, descendants of those people, having achieved all of this in a cosmic eye blink. What might our descendants achieve in the next 10,000 years? The next million? If we don't destroy ourselves, if we navigate the challenges of climate change, nuclear weapons, artificial intelligence, and other existential risks, then the future is genuinely open. We could become a spacefaring civilization, a multi-stellar species, explorers and settlers of the galaxy. But it starts with small steps. It starts with missions like Voyager, which even now are entering interstellar space. It starts with robotic probes to Mars and the outer planets, learning to operate in deep space. It starts with discussions like this, thinking through the possibilities, challenges, and implications of interstellar travel. It starts with choosing to care about the future, to invest in projects that transcend our individual lives, to think of ourselves as part of something larger and longer lasting than our brief existence. So, to wrap up this exploration of interstellar travel to Proxima Centauri, let me summarize the key points. First, the distances are almost incomprehensible. 4.2 light-years sounds close, and it is by cosmic standards, but it represents about 25 trillion miles, roughly 6,000 times farther than Pluto. With current technology, reaching Proxima would take tens of thousands of years. Second, several technologies could potentially make the journey faster. Laser-pushed light sails could reach 20% of light speed, arriving in about 20 years. Nuclear pulse propulsion or fusion drives might achieve similar speeds. Generation ships or suspended animation could make slower journeys psychologically tolerable. Each approach has profound challenges but might be achievable with sufficient development. Third, the destination is fascinating. Proxima b is a potentially rocky planet in the habitable zone, the right distance for liquid water. Whether it actually has water, an atmosphere, or life is unknown, but the possibility makes it an incredibly compelling target. Studying another planetary system close up would revolutionize our understanding of planets, stars, and the potential for life. Fourth, the challenges are not just technical but also political, economic, and philosophical. An interstellar mission requires resources, long-term commitment, global cooperation, and careful ethical consideration. It would profoundly affect human culture and self-perception. Fifth, the benefits extend far beyond the destination. The technological spin-offs, the inspiration for future generations, the shift in perspective about our place in the universe. These could be as valuable as any scientific discoveries at Proxima Centauri. And finally, this is a multi-generational project. We won't launch an interstellar mission next year or next decade, but we can start laying the groundwork now, developing technologies, building infrastructure, and fostering the long-term thinking required for such an endeavor. What we do today makes it possible for future generations to do what we cannot. There's a quote often attributed to the ancient Greek proverb: "A society grows great when old men plant trees in whose shade they shall never sit." An interstellar mission is the ultimate version of planting trees for future generations. We might not live to see the spacecraft arrive at Proxima Centauri, but we can contribute to making it happen, giving our descendants the gift of new worlds to explore and understand. The night sky has fascinated humans since we first looked up and wondered what those points of light were. For most of history, the stars were unreachable, literally and figuratively beyond our grasp. We could only observe and imagine. But we've entered an era where the impossible becomes difficult and the difficult becomes achievable. We've sent robots to every planet in our solar system. We've landed humans on the moon. We've operated rovers on Mars for years. We've sent spacecraft beyond the edge of our solar system into interstellar space. Reaching another star is the next frontier, the next great challenge. It's difficult, perhaps the most difficult thing our species has ever attempted. But difficult is not impossible. With time, effort, ingenuity, and commitment, we can extend our reach to Proxima Centauri and beyond. And when we do, when the first images arrive from a probe orbiting Proxima b, when we see the orange glow of Proxima Centauri from close up, when we study the surface and atmosphere of a world orbiting another star, that will be one of the greatest moments in human history. It will be the moment when humanity truly became an interstellar species, when the stars shifted from distant dreams to reachable destinations. I hope I live to see it. I hope you do too. And if we don't, I hope we can contribute in some way to making it happen for those who come after us. Because this is bigger than any individual. This is about what humanity can achieve when we dream boldly, think deeply, work together, and commit to goals that transcend our brief time on Earth. The stars are waiting. Proxima Centauri is waiting. 4.2 light-years away, a tiny red star glows quietly, orbited by at least one planet that might, just might, be a world we could visit, study, maybe even inhabit someday. The journey will be long and difficult, but it's a journey worth taking. Thank you for taking this journey with me through the possibilities, challenges, and implications of interstellar travel. The future is unwritten, and what humanity achieves depends on what we choose to pursue. I hope we choose the stars. Now, if all this talk about traveling to Proxima Centauri at 20% light speed has you wondering, what would it actually be like to hit full light speed? Click the video on the screen, because the physics get wild, and trust me, you won't believe what happens to time, space, and reality itself.